To master basic calculus, you rely almost entirely on the rules of algebra. But the moment you attempt to calculate integrals across higher dimensional spaces, you are forced to confront pure, unmeasured geometry. For decades, mathematics students have turned to Walter Rudin's Principles of Mathematical Analysis to navigate this exact problem. For most of the text, Rudin keeps you firmly grounded in equations and limits. But late in the book, he pivots away from numbers and begins dissecting the shapes of spaces themselves. This shift happens deep into Chapter 10, beginning on page 266 with a section titled Simplexes and Chains. This section addresses a central challenge. How do you define a warped continuous geometric surface so strictly that a pure algebraist could calculate it without needing a visual aid? To achieve this, we have to build a rigorous mathematical toolkit from the ground up. We will start with a single dimensionless point, and we will build toward a defining equation in topology. We have to do this because without these precise geometric building blocks, generalizing Stokes Theorem and executing integrals over complex n-dimensional spaces is impossible. In basic one-dimensional integration, the standard unit of measurement is simple. It is a straight interval on a number line, bound between 2 points A and B. When you jump into 3 or 4 dimensions, that simplicity vanishes. You are suddenly dealing with curves, gaps, and boundaries that bend in multiple directions at once. To restore order, mathematicians created the concept of a simplex. A simplex is the simplest geometric shape possible for any given dimension. In mathematical notation, this idealized base shape is the standard K-simplex, denoted as QK, where K is the number of dimensions. QK acts as a universal geometric ruler. If we can master how integration works on this simple shape, we can eventually map that understanding onto more complex surfaces. Let's build these rulers. We start at the 0 simplex, Q0, a single point at the origin. The 1 simplex, Q1, stretches a segment 1 unit out. The 2 simplex, Q2, pulls that into a flat right triangle. The 3 simplex, Q3, pushes into a solid tetrahedron. Every internal point follows a strict algebraic rule. Coordinates must be positive, ui greater than 0, and their sum cannot exceed 1, sigma ui less than 1, creating the bounding faces. While we process these visually as triangles and tetrahedrons, Rudin's text treats them entirely as a pristine set of algebraic constraints. However, the standard simplex has a specific constraint. It is anchored to the origin, while practical integration requires us to measure spaces located anywhere in a coordinate system. To move it, we use an affine simplex, mapping our standard shape to a new location. We define this shape entirely by its vertices. Sigma equals the ordered list P0, P1, and P2. Using Rudin's linear mapping formula, P0 acts as a new local origin, with vectors stretching the shape outward. Once anchored, every point inside that new triangle is calculated as a weighted average, a convex combination of those 3 vertex anchors. Using affine transformations, we have localized our standard ruler, allowing us to place a perfectly measurable simplex anywhere in higher dimensional space. But placing a shape is only half the process. In calculus, integrating along a path requires tracking direction. We establish direction, or orientation, by the order we list vertices. Listing them as P0, P1, P2 creates a counterclockwise flow. Rudin applies a strict algebraic rule. Swapping any 2 adjacent vertices reverses the orientation, making the simplex negative. With these oriented floating triangles, we can start combining them to construct larger structures. When you glue multiple simplexes together, you create what is called a chain. A chain is written as a formal algebraic sum. The integer coefficients dictate how many times a piece is counted, and the signs dictate its orientation. A chain is a formal algebraic sentence that defines a specific topological surface. This brings us to a mechanical problem. If a computer only reads the algebraic list of vertices, how does it locate the outer perimeter? The solution lies in the boundary operator, denoted by the symbol del. Rudin defines the boundary operator with this equation. The hat instructs you to delete that specific vertex. Running our triangle through this machine systematically deletes vertices one by one, generating 3 distinct line segments. The alternating minus sign forces the middle segment to flip its orientation, connecting all edges head to tail in a continuous circuit. The boundary operator converts the geometry of a solid surface into a pure algebra equation representing its outer shell. This brings us to a fundamental theorem in this framework. The boundary of a boundary is zero. Geometrically, the boundary of a solid disk is a closed circle. Trying to find its endpoints reveals nothing. It has no beginning and no end. Rudin proves this mathematically by applying the boundary operator twice, which results in a double summation. The proof hinges on orientation. When you apply the operator twice, you delete two vertices. Because of the alternating signs, deleting vertex I then vertex j produces the opposite sign as deleting j then I. Because every edge combination appears exactly twice with opposing signs, the entire equation cancels itself out to zero. We have just demonstrated a core property of algebraic topology, that a boundary has no edges, using basic algebraic cancellation. Look at the exact pathway we just walked. We took a visual progression from a point to a surface to a closed edge and built a mirror image of it entirely out of algebraic text. Simplexes gave us a baseline unit. Affine mappings allowed us to localize them. Chains allowed us to glue them into complex structures. Finally, the boundary operator ensured this framework was airtight, establishing the parameters required for the generalized Stokes theorem. By translating shapes into algebra, Rudin establishes the mechanics for evaluating integrals over complex forms with mathematical precision. Navigating pure mathematics at this level requires immense focus. If you followed the logic this far, you are doing great. If this breakdown helped clarify the concepts, please hit the like button and subscribe to Maths Ada. In our next videos, we are going to take these chains and boundaries and put them to work, continuing our breakdown of Chapter 10. Thanks for watching, and I'll see you in the next one.